Hi everyone. If I haven't scared you away with the introductory video to 7.3, now we're going to work through some examples of varying difficulty. I'm going to pull these directly from the textbook. So the first thing we're going to look at is the integral of x over the square root of 36 minus x squared dx. And this is book problem number 6. Now, when we're looking at a problem like this, we have to triage the problem. Is there a u substitution? Actually, in this case, there is a u substitution. I'm going to do it with inverse trig substitution to show how the method works. The pattern I see here is 36 minus x squared, which is a squared minus x squared, with a equal to 6. And the method says when I see a pattern like that inside of a square root, what I should do is let x be equal to a times the sine of u. So let's actually build the substitution we're going to use specifically. X is going to be equal to 6 times the sine of u, and dx is going to be 6 times the cosine of u du. Because I'm going to need the relationship later, I'm going to write that u is equal to the arcsine of x over 6. And now I'm just going to build the substitution that's supposed to happen here. So x is equal to 6 times the sine of u, and dx was equal to 6 times the cosine of u. And on the bottom, I've got a square root now of a 36, and if x is equal to 6 sine u, then x squared is equal to 36 sine squared of u. The whole reason I did that was so that I could use a Pythagorean theorem down here. So this is going to be equal to the integral of 6 times the sine of u over the square root of 36 times the square root of 1 minus the sine squared. And that just becomes 6 times the sine of u. On the bottom, I'm going to get a 6. The square root of 1 minus sine squared is the same as the square root of cosine squared, which is just cosine. And because this is one of the early problems in the book, we can see that we get these nice cancellations where those cancel, and this entire integral collapses into 6 times the sine of u du. And that integral is just negative 6 cosine u. Now to finish this up, I'm going to use the right triangle method, because I want to replace this with an expression in x. And I'm not done because I haven't gotten rid of the u's yet anyway. So what was u? U was the arcsine of x over 6. So all of this together is going to tell me that I've got the integral that I started with, x over the square root of 36 minus x squared dx, I have reduced to being equal to negative 6 times the cosine of u plus c, but the u that I used was equal to the arcsine of x over 6. So all of this minus 6 cosine of the arcsine of x over 6. And now I've got to build that right triangle that I was interested in building. So arcsine is an angle, and it's an angle that corresponds to a right triangle that has the opposite side being x and the hypotenuse being 6 because it's a sine. So I build my triangle. This thing right here is theta. The triangle that it goes with, because it arises from a sine, has x on the opposite side, and it has 6 on the hypotenuse, and that means this side is 36 minus x squared. That's comforting because that's actually the expression that appeared in the original integral right here. And so what is the cosine of that angle? Well, the cosine is the adjacent side over the hypotenuse, and so all of this is minus 6 times the adjacent side of that right triangle, which is 36 minus x squared, divided by the hypotenuse, which was 6. Those cancel, and you just get minus the square root of 36 minus x squared. Same answer you would get if you had done this with a u substitution instead. Okay, example 2, I'm going to do an example where we have to manipulate a rational expression so that we can make the function look like a trig function. So for this one, we're going to look at dx over the square root of x squared plus 2x plus 5. Now this screams out that this is going to be some kind of tangent substitution because it almost looks like x squared plus a squared, but it's not in the right form yet because we've got this extra x floating around. And so the tool that we're going to want to use here is to take x squared plus 2x plus 5, and we want to rewrite it as something squared plus something. And I need to know what those numbers are. You can use completing the square or your familiarity with some of these basic patterns that come from pre-calculus to notice that x squared plus 2x plus 1 is a perfect square. So I'm going to rewrite this as x squared plus 2x plus 1 because that would be a perfect square. Well, I'm not allowed to just add 1 to an expression, so I'm also going to take it away, and then that 5 was already there. This factors as x plus 1 squared plus 4. I'm almost ready to use an inverse trig substitution, but I still have this x plus 1 right here. I'm going to get rid of it by making a substitution like, I don't know, t is equal to x plus 1, so that dt is equal to dx. And now the integral is the integral of dt over the square root of t squared plus 4, and that is an integral I can use the tangent substitution on. So our pattern tells us that this is an x squared plus a squared with a is equal to 2. And that means the substitution I'm going to make is I want t to be equal to 2 times the tangent of u. I'm also going to need to know that dt is equal to 2 times the secant squared of u du. Now let's make the substitutions. This is equal to 2 secant squared u du. And on the bottom, I'm going to get the square root of 4 tangent squared plus 4. And 4 tangent squared plus 4 was chosen specifically so that I would get a square root of 4 times a square root of tangent squared of u plus 1, which is a secant squared, and the square root of secant squared is secant. So this entire thing collapses to 2 times the secant squared of u du. The square root of 4 is 2. The square root of secant squared is secant. Algebraically simplifying, we get the integral of secant, which is the natural log of the secant of u plus the tangent of u plus c. Of course, u is not what we were after. So if t was equal to 2 times the tangent of u, then u is equal to the arctangent of t over 2. And so all of this becomes, this is going to get ugly, the natural log of the secant of the arctangent of t over 2 plus the tangent of the arctangent of t over 2. Well, at least those functions are inverses and they just cancel. But t itself was something that we'd substituted because recall that t is equal to x plus 1. So I have to get this entire expression back into x's, and so you get the natural log of the secant of the arctangent of x plus 1 over 2 plus x plus 1 over 2 plus c. What I've done here is I've eliminated the tangent and the arctangent because those are inverse functions. If you wanted to finish the problem, you would then use the right triangle method on this chunk right here. I'm not going to show that right now, but that is how you would finish the question. So this is an example of a difficult question. Okay, because we had to use algebraic manipulation, and then we can see that it's a long pathway from the beginning to the end. So practice your homework. Please come to office hours for these because it's much easier for me to work through problems and give you hints than it is to grind you through hours of examples of how this stuff works. I can't cover every possible case. If you're having trouble, come talk to me. All right, see you for 7-4.